Hey everybody, let's talk about dimensional analysis, also known as the factor label method. We cannot impress upon you enough that this is one of the most important concepts we'll learn all year. Why? Because we will use it in literally every single unit, right? So you want to build yourself a really strong foundation with this method and how it works, and by all means get practice. And if you're having difficulties, definitely see us for help, but this is something that we'll use all year. So dimensional analysis is a way that we can convert from one unit to another, and it uses these things called conversion factors. So a conversion factor is basically a ratio. It's a ratio that comes from an equality. So for instance, we know that 12 inches is equal to 1 foot, right? And so let's do something. Let's solve this thing for the number 1. And we're going to do that two different ways. So what if I took that and I divided both sides by 12 inches? Right? If I divide both sides by 12 inches, then 12 inches over 12 inches is simply the number 1, and that is equal to 1 foot over 12 inches. Conversely, though, couldn't I have done the opposite? Couldn't I have divided both sides by 1 foot? Remember, if you do something to one side in math, you have to do the same thing to the other side. So 1 foot over 1 foot is 1. So we would get that 12 inches over 1 foot is equal to 1. And so you'll notice that both of those things, because they're both equal to 1, are obviously also equal to one another. And both of those things represent that equality that 12 inches equals 1 foot. But because they're all equal to the number 1, and here's the often overlooked but critical component of dimensional analysis, we can multiply any number in any problem by a conversion factor, by a ratio like this. And we're actually not really changing the number, we're changing the unit, right? Because mathematically we're just multiplying by the number 1. And so this is a way of converting from one unit to another, and you'll notice that that conversion factor, that ratio, can be written either with 1 foot on the top or 1 foot on the bottom, and this becomes really important because we are going to have to cancel our units if you see, as you'll see in a second. So there's some questions that you can see there that we're going to ask ourselves as we get into more difficult problems. We're going to ask what we know with certainty, what we're trying to find, and what conversion factors, what ratios do we know like these along the way to get us there. Just as a little side note, if we have any metric units that have prefixes in them, because they have prefixes in them, we're going to have to go back through the base unit. So that's what we're talking about here in letter D. Those metric units, we need to go back through the base unit. We will see that whenever we get into some example problems below. There are also some important little relationships to know, basically between metric and English system. We give you some of those that you're already aware of on the back of your periodic table. So you have some of these equalities already for you, and they're a really good resource to convert from one thing to another. So let's do all this. Let's define what we know. Let's define what we don't know. Let's define what we're trying to find. And these are steps that you may not take in every single problem as you get used to this, but to start, I think it's worth doing. So we know in pink that we have 45.5 grams of calcium chloride. Just as a side note, calcium chloride is CaCl2. It'll be a little bit easier to write that instead of writing out calcium chloride every single time. We are trying to find in blue that mass in kilograms. Right? So we know that we have 45.5 grams to start. We're trying to find kilograms. And so there must be some relationship that we know, right? And let's write that in green. We know that there are 1,000 grams in 1 kilogram. So with those three pieces of information, we can set ourselves up a conversion that works really well. Now, there are different ways of setting up these conversions. Different people prefer different methods. We don't care with which method you use as long as you're using dimensional analysis. So I'm going to show you the different methods in these different problems. So the method that I typically use, and again, this doesn't mean you have to use it, is to set up a big line, and this line basically represents a fraction. And every single vertical line is going to represent a new fraction. So it's a place where we're doing a new kind of calculation. And we're always going to start with what we know. So in this case, I'm always going to use pink for what we know. So we know that we have 45.5 grams of CaCl2. And our goal is to cancel out that unit. Now, how would we cancel out this unit in the numerator? We'd put the same unit in the denominator. We'll get there in a second. We want to cancel out that unit and eventually arrive at our end destination, which is kilograms, right? That's where we're trying to get to. So ultimately what we want to do is utilize our green conversion factor to get us to our ending unit, right? So let's see how we could set that up. Remember the conversion factor 1,000 grams equals 1 kilogram can be written in two different ways, right? This could be written as 1 kilogram over 1,000 grams. We've already proved to ourselves that that equals 1 up top. Or 1,000 grams over 1 kilogram. And so you need to ask yourself, which way should we put that in? And if you look back to what's here in pink, we know already, we know that we have to put grams of CaCl2 on the bottom. Why do we have to put grams of CaCl2 on the bottom? Because it must cancel out with the grams of CaCl2 that's already in place in the numerator up here. Ultimately, what we want to do is get rid of these, like so, cross those out. And we want to convert into, on top, our new unit, right? So what's our end goal? Well, our end goal there is kilograms, and that's in blue, right? We want to get to kilograms. The only question left is what numbers can I put in to make that true? And the numbers that you can put in are right here in green, right? So which one has kilograms, right? Kilograms over grams, it's this one. So we know that 1 kilogram is equal to 1,000 grams. To solve this mathematically, what we're going to do is basically multiply all of our fractions together. So we're going to take 45.5 times 1, which is 45.5, and then divide by 1,000. And when we do that, we will get the answer 0.0455 kilograms. And you'll notice that we've been very careful to keep our units. You'll notice that our units have canceled, and the only unit that's left is this blue kilograms, and so that's why that is the unit that we write here. And again, we'll get more practice at this and get more of a hang of it. So let's try micrograms in 0.0025 grams of vitamin A. Okay, so let's write down what we know, what we don't know. So we know in pink that we have 0.0025 grams of vitamin A. That's good. What are we trying to find? Well, we are asked how many micrograms. That's what we're after. And what do we know? Well, if you go back to your metric prefixes, we have a relationship. We happen to know that 1 million micrograms, or 10 to the 6th, micro has this really funny little mu symbol, micrograms is equal to 1 gram. So let's see if we can utilize that in a similar way. I'm going to show you the other way that people sometimes write this. Again, you can select which way works best for you. Other people like just making individual fractions. So here's a fraction. We're going to start with what we know, which is 0.0025 grams of vitamin A. So 0.0025 grams. I'll call vitamin A VA for vitamin A. And then we need a new fraction. So you're going to multiply and a new fraction. And again, either of these methods works. We do know some things, right? We know on the bottom that we want to cancel out grams of vitamin A. Why do we know that we're putting that on the bottom right here? Because we know that this unit must cancel. So the way you do dimensional analysis is you always just cancel units as you go along. And we know that up top, our end goal is micrograms. So we want to get to micrograms, which is that strange symbol of vitamin A. And it turns out in green, we know the relationship that's going to take us there. We know that 10 to the 6th micrograms is equal to 1 gram. You'll notice that conveniently our units cancel. Grams VA, or vitamin A, cancels. We're left with micrograms vitamin A, which is what we want. And when you do this math, you will get 2,500 micrograms of vitamin A. Another thing that we haven't discussed so far, but we should be aware of, is significant figures. So when we're doing multiplication division, we always want to have our number of significant figures that we start the problem with match our ending number, right? So let's do significant figures in orange. This number that we started with has 3 significant figures. That's why our ending value has 3 significant figures. This number that we started with here has 2 significant figures. Our answer has 2. So we always want that to match up. All right, let's try another. We are going to start with 3.5 moles. We don't know what a mole is yet, but it's just a unit that we can cancel out. We want to get to n mole. N mole stands for nanomoles. So if you look to your metric prefixes, it turns out that there are 1 times 10 to the 9th nanos, so 1 times 10 to the 9th nanomoles in 1 mole. We'll utilize that to our advantage. Let's start with what we know, 3.5 moles. I'm going to go back to the other method of writing out fractions, so we'll do it this way with a long line. We know that we have 3.5 moles to start with. And let me actually make that pink just to stay in line with what we've been doing so far. So this is our starting value, 3.5 moles. We know right off the bat that moles must go on the bottom. Why? Because we have to cancel it out. What are we trying to get to on top? Well, we're trying to get to nanomoles, n mole. What numbers are we going to put there? Well, fortunately, we have this conversion factor in green. We know that there are 10 to the 9th nanomoles in 1 mole. Now, this is a good opportunity to show you, what if you did this? What if you put 10 to the 9th on the bottom? Right? So what if you did this? Well, that's not true, is it? There are not 1 billion moles in 1 nanomole, right? Or think of a nanometer. A nanometer is really, really tiny, right? There are not a billion meters in 1 nanometer. So that's clearly false. So we might get tricky and we'd say, well, I need to flip those around, don't I? Let's flip everything. So we're going to put 10 to the 9th on top. Here it comes. We are going to put that on the bottom, our 1, and let's flip these while we're at it. We're going to put moles on top. We are going to put nanomoles on the bottom. And that doesn't work either, does it? Because at the end of the day, if you do that, look at what your units are going to turn out to be. You're going to have moles times moles on the top. Your units here are going to be moles squared over nanomoles, which is not what we want, right? Nothing's canceling out, so that's not ideal either. So there are really only 2 things you have to check with the dimensional analysis to ensure that you have this correctly. Number 1 is you have to make sure your units cancel. So let's do that first. Our moles is on the top. We're going to put moles on the bottom to cancel out. That's step 1. That also results in putting nanomoles on top. Step 2 is to make your equation correct. So how do you make this correct? Well, it's not 10 to the 9th down here. We just proved that to ourselves. It's 1 mole equal to 10 to the 9th nanomoles on top. So as long as your units cancel correctly and all of your equalities are true, all of your ratios are true, you will arrive at the end of the day at the correct answer. So in this case, it's 3.5 times 10 to the 9th power nanomoles. We should check our significant figures in orange. You'll notice we started with 2 sig figs right there, 3.5. We ended with 2 sig figs right there because we don't count times 10 to the 9th for scientific notation. All right, let's try another one. And if you've been wondering, you probably haven't been, but if you've been wondering when we'll encounter a problem that has this little issue with it, be prepared. So, in number 4, we have some things we know. Right? We know that we have 5.2 centimeters magnesium. Magnesium, as a side note, is Mg. We want to convert that into millimeters. So, I'm going to bypass writing down stuff in green right now for a very specific reason. Let's start with what we know. First off, I'll get my table set up. We know that we have 5.2 centimeters of magnesium. So 5.2 cm, magnesium is Mg. We also know that we need to cancel out that unit, right? So in the bottom of this one, in the denominator, we're going to put centimeters of magnesium. And we know ultimately from the problem that we are trying to get to millimeters of magnesium. And so the question you have to ask yourself is, how many millimeters are in a centimeter? And the answer is we don't know. You might know, but this is kind of an easy one, right? These are units that we're familiar with, centimeters and a millimeter. What if I asked you how many picometers are in a hectometer, right? Then you'd be like, I'm not really sure. So the rule that we want to use is that we cannot go between two units that have prefixes. So millimeters is a prefix, centimeters is a prefix. What we need to do in this situation is go back to the base unit. So we are going to leave the pink centimeters of magnesium on the bottom because we need to cancel it out. But this time, we're going to go to a special unit. We are going to go to meters of magnesium because we know from our metric table that there are 100 centimeters in 1 meter. We then have units of meters on the top. So thus far, our centimeters has canceled. That's good news. We now have meters on top. We need to cancel meters. So let's put meters on the bottom. Meters magnesium down here. What are we trying to get to in the problem? Well, look at it right there in blue. We're trying to get to millimeters of magnesium. How many millimeters are in a meter? Look to your table. There are 1,000 of those millimeters in 1 meter. This was an important step because now our meters cancel. The only thing that's left uncanceled at the end of the day is millimeters. And you might ask yourself how we solve this. Well, this is just a big set of fractions. So the math that you want to do is 5.2 times the fraction 1 over 100 times the fraction 1,000 over 1. Or said another way, multiply all of your numerators and then divide by all of your denominators. So it's really 5.2 times 1. You don't need to plug that in your calculator. Times 1 doesn't do anything. Times 1,000 divided by 1,000 and divided by 1. But again, the second 1 doesn't matter. So when you do all of that math, you'll notice the only unit that's uncanceled is millimeters. We will end up with 52. Let's keep this black. We'll end up with 52 millimeters of magnesium. And the last step here, let's check our significant figures. You'll notice that we started the problem over here with 2 significant figures. That means our answer is going to have 2 significant figures. All right, let's try one more. Again, we're going to have multiple steps here. We can write out fractions like we did before if we'd like. Let's define what we know. We know that we have 1.60 milliliters. Our end goal is to get to microliters of ethanol. We'll abbreviate ethanol in a second. And let's see how we can get there. So I'm going to set myself up a fraction line. And we're going to start with what we know, 1.60 milliliters. 1.60 milliliters. We're going to abbreviate ethanol, ETOH. OH is an abbreviation for alcohols. We're then going to multiply by a fraction, and right off the bat, we know something about that fraction. We know something really important, which is its denominator. We know that down here in the bottom, we are going to put milliliters of ethanol. Why do we know that? Because it needs to cancel out. So the pinks are going to cancel out. Now we're trying to get to microliters, right? So you'd say, well, let's put microliters up top. But the problem is we don't know how many milliliters are in a microliter, right? We have 2 prefixes, so we can't do this. What we need to do is go back to the base unit. We do know how many milliliters are in 1 liter of ethanol, and it happens to be 1,000 milliliters in 1 liter, or 10 to the third. Milliliters ethanol will now cancel. Now we have liters of ethanol up top. We know something about our next fraction. Our next fraction must have liters of ethanol in the bottom. Why? So it will cancel. You'll notice I'm not putting in a number yet. I'm just getting my units set up. And we know that at the end of the day, the problem wants us to get into microliters of ethanol. Now decide what numbers make this true. Well, the numbers that make this true are 10 to the 6th, 1 million microliters in 1 liter. And check out what's happening unit-wise. Milliliters is canceling. Liters is canceling. We're only left with microliters. If you do the math here, again, you're just multiplying fractions. At the end of the day, you will get a value 1.60 times 10 to the third microliters of ethanol. And again, we should check our significant figures. we started off with 3 significant figures right here. We're going to end with 3 significant figures. So this lesson on dimensional analysis, you'll notice there are multiple ways to do it, but in every single case we're defining what we know, what we're trying to get to, we're checking our sig figs, we're being really careful to cancel out our units, we're being really careful to make sure that each one of our qualities is true. This technique is extremely important, so if you're confused at all, you can find more resources online. We're obviously going to have more practice with this. Definitely ask us questions. We want to make sure we're on the same page because this keeps coming back over and over and over again all year.